Welcome back to ECE 442-542. This is the third segment of Lecture 2 in Unit 7. This is Lecture 7.2c, where we are going to run through some examples of how we might design PID controllers, and actually we'll sort of work our way up to that by looking at PI controllers applied to a first-order plant that's stable, but then it might have some uncertainty in the plant dynamics. We'll then look at another plant that's unstable and stabilize that with a PI controller. And then we might say, oh, do we need to look at a PID controller? Do we need more flexibility? Do we need more than PI action in this control scenario? Let's start with the first example. As I said, let's look at a stable plant. It has a pole at 0.75, and we now, if we wanted to, we could ask what happens in the closed loop with a P controller. With a P controller in the closed loop setting, our closed loop transfer function, now our controller is in cascade with the plant, and it's in a negative unity output feedback configuration. We could now have K G of Z over 1 plus K G of Z. And I hope you can see the root locus for that. Now the root locus is right there, and you can locate the closed loop pole anywhere you want between 0.75 and -1 and produce a stable closed loop system. Obviously you may not want your closed loop pole over here. You might prefer to have it closer to the origin. But what's going to happen to your steady state accuracy? Now, with a proportional controller, you will have some error between where you want your output to go, maybe specified, which would be specified by your reference input, and where you actually can end up. So now there will be a steady state error. Well, to get rid of that steady state error due to constant inputs, we might use a PI controller. That now forces and so now we're walking through the different versions of PID controllers. We looked at a P controller. Maybe we didn't like the steady state accuracy that resulted from that. Now let's ensure that we have zero steady state error due to constant inputs by introducing an integral action, and we'll do that through a PI controller. Now we can put a pole. That's immediately done. Let's now say that our C of Z for this particular system, and one way to make it pretty easy to think about in terms of sketching a root locus, we know that this is now at 0.75. Why don't we just let our 0 cancel that pole, and now our root locus diagram looks similar to what we had before, but now we are assured of having zero error due to a constant input, and we can now locate maybe our closed loop pole there, or maybe we want to put our closed loop pole right at Z equal to 1/2. That can be done. We now look at our combination of C of Z with G of Z, and that's what we are now sketching the root locus for, is this loop gain transfer function CG, which if we cancel the pole at 3/4 with this 0 at 3/4, that's allowed. We can cancel poles and zeros inside the unit circle. We now have K over Z minus 1. And that root locus is easy to sketch, so that our closed loop system is now not kg, it's cg. So now we have cg over 1 plus cg, or that now becomes, canceling the numerator's denominator and the denominator's denominator, which are both z minus 1, we have k over z minus 1 plus k. Or our closed loop pole, we only have one, is determined by the denominator of capital T of z, our closed loop transfer function, and we can find that closed loop pole by finding the characteristic equation or setting the denominator polynomial equal to 0. If we now solve that for z, we now can say that, oh, the pole location, z, is determined by what we choose for k. And in this case, we're guaranteed steady state accuracy or zero error due to a constant because of the integral behavior of this controller, and we can pick the k to determine the speed of response. Here we could set k to give us our closed loop pole at 1/2, and that would mean then that our natural behavior would be governed by this mode of 1/2 n, or our closed loop behavior. What happens though if somebody says, oh, I don't know, my plant could be 0.75, it could be 0.7 in terms of its pole location, maybe it's at 0.8, I don't know, and now we've designed it based on sort of the average. We've said, oh well, let's design a controller for this plant that has a pole at 3/4. Now what do we do? Well, let's just look at what happens. How robust is our design that we just created? Suppose the true pole of our plant was at 0.7, and we've designed our controller to have a 0 to cancel what we thought was the pole at 0.75. Well, now let's see what happens to the root locus based on this true plant that has a pole at 0.7 and this controller design that we just produced. So now we have a pole at 1, that's the integral action. We have a 0 at 3/4. It's not quite on top of that pole now, is it? But what's the root locus diagram for this? Now we can just cut up our French bread, our real axis, into the different segments and ask which segment belongs to the root locus. We know this segment does, and we know this segment does. That piece between 0.75 and 0.7, which is hard to see, but that segment on the real axis does not belong to the root locus, nor does the segment from 1 to plus infinity. We know that that pole at 0.7 is going to zip off to minus infinity, and what we want to do is make sure it doesn't go beyond -1, because then we would be unstable. And what do we know about this pole that starts at 1? Well, it's going to approach that finite 0 and be basically sort of absorbed or annihilated by that 0 if we really cranked up the gain. But we're not going to crank up the gain too much. Maybe we still have that pole, and the gain is now determined maybe before we set it at 1/2 based on the assumed pole location of 0.75. Now this pole may be right there, which is getting close to that 0, and so you have almost a pole 0 cancellation there, and the effective dynamics are determined still by that pole, closed loop pole, given by the triangle. So this triangle is now our closed loop pole, and in fact we have two closed loop poles. We have two open loop poles, one of the true plant at 0.7, one due to the controller pole at 1, and the triangles then are determined by the gain value k that we select. But you can see that the behavior is not going to be that different than what it was here, so our design using this PI controller is fairly robust to uncertainty in our plant, or uncertainty in our true system. Okay, that's if our true plant was at 0.7, but now somebody said, oh, in fact, your true plant had a pole at 0.8. Oh, now what do you do? So now your true plant is 1 over z minus 0.8, and you've still designed your system based on that plant model that you assumed, and that had a pole at 0.75. And you're using a PI controller, so you know you have a pole there, and now you have a 0.05 away from 0.8 because it's at 0.75. Now what happens? Is this completely going to mess things up? This is our story, isn't it? What was our story? 2 poles to the right of a 0. That's what we have here. What's the root locus look like? How many root locus branches do we have? We have 2. We have one branch that starts on the pole at 0.8. We have another branch that starts at the pole at 1. They approach each other, and they will then go around. That's our diagram, root locus diagram. One will go towards that finite 0. The other one marches off to negative infinity, and we know better than to crank up the gain beyond -1. And in fact, if we designed our controller based on a pole at 3/4, we probably now have a closed loop pole there. And where's our second closed loop pole? We know we have 2 because we started with 2 open loop poles. In order for these 2 branches, one to already be going to the left, the other one now has to be going to the right, and it's now getting close to or nearly on top of that 0 that we had established before at 0.34. So that now we have again this near pole 0 cancellation, and the deltas correspond to our closed loop poles. One of those closed loop poles is nearly annihilated by the 0 at 3/4. The other one is close to where we were hoping it to be, which was around 0.5. So this design, using a PI controller for maybe a nominal plant of g of z equal to 1 over z minus 0.75, is actually robust to uncertainty in our system, whether that uncertainty was a faster pole in our real plant or a slower pole. We're still ending up with that triangle on the left in almost the same location as where we had it from our original design for that particular system. That's now one design, and we didn't even get all the way to PID. We went to PI, and that may give us acceptable behavior. What if we now start with an unstable system, a system that has a pole outside the unit circle, and we still want to have 0 error due to a constant input? Let's see if we can achieve that based on a PI controller structure. We now have our system possessing a pole at 2. We said, oh, PI controller, we now have a pole at 1, and beta is at our discretion. We can now pick beta to be wherever we want it to be. And where do we want it to be? Well, we definitely don't want it to be there, because then we would have an unstable closed loop system. We don't want to put it here, because then we would have a guaranteed unstable system. We probably want to put it somewhere there so that we now have our story again. We now have 2 poles to the right of 1, 0. And this sketch may not do justice to what we know. We know that that circle is centered at that 0 location. So I've drawn this to where the left side needs to be a little bit further to the left, but we have two branches. They start at 1 and at 2. They approach each other, and then if we crank up the gain enough, we can stabilize this system so that we would have closed loop poles at many different possibilities that might still be stable. We could put our closed loop poles there, or we might put our closed loop poles there, and there are many different reasons for locating them at the triangle location, at the square location, maybe at the star location. For me, I would probably prefer the triangle location, because having poles near -1 sometimes can be problematic, and that's where that leftmost box is going, and it might actually be more visible because that box, if it's close to the 0, may be somewhat annihilated by that 0's behavior, because what do 0's do? They zero out a response. So this is now, though, the one way to select a stable closed loop system. We can pick beta to produce the desired root locus path, and K is used to fix the dominant poles. Suppose somebody says, well, I want my dominant poles, my z deltas, to be at 0.9 plus and minus j 0.1. So they're now saying that they want their dominant poles somewhere in there. Is that even possible with a PI controller? So now let's see. Well, now we can use our root locus design knowledge to determine, can we end up with the root locus branches going through these triangles at 0.9 plus and minus j.1. We know that for a PI controller, we have one pole at 1. Our plant had a pole at 2. We just don't know where to locate that 0 that's given now at a location of beta, that real 0. We can actually use the phase angle condition to place beta, or to find where beta is, if it's even going to be possible to locate our root locus branches, having them pass through those triangle locations. So we'll use the phase angle condition. What does that mean? That means that the angles contributed by these two poles and a 0 need to sum to minus 180 if they're on the root locus. So we now know from the phase angle condition that the angle of the 0 minus the angle of the two poles, it's just the pole that's the red X and the blue X. It's not, you don't consider the contribution due to that lower triangle. That's a branch on the root locus. That's not one of your open loop poles. So you don't use that in the phase angle condition. You have theta z is minus the sum of theta p1 plus theta p2. That needs to equal minus 180 degrees. And theta p1, I think we can see, because we located this z delta at 0.9 plus j 0.1, so that that triangle is 45 degrees if we measured it from the left real line segment from the pole at 1. So that's 45 degrees less than 180 degrees. Theta p1 is 135 degrees, 180 minus 45. We now need to compute theta p2, but we can do that. We know how far it is horizontally from 2. It's 1 plus 0.1, because that triangle is at a real location of 0.9, and it has a vertical height of 0.1. What we don't know is where that beta, where that 0 is located, and we're trying to then find that theta sub z. theta p sub 2 is 180 minus this acute angle that has a vertical height of 0.1 due to the j 0.1 and a horizontal distance of 1 plus the distance to get us from 1 to 0.9, which is 0.1. So we now have inverse tangent of 0.1 over 1.1, which is a little bit more than 5 degrees. We take that away from 180 and we're left with 174.8 degrees. That's theta p2. We can plug that in here. We know what theta p1 is. That's 135. So do we achieve a reasonable value for theta sub z? We have theta sub z minus theta p1. That was 135 degrees. Theta p2 was 180 minus 5.194. The reason I wrote it in that expanded form is because this minus 180 cancels the minus 180 on the right. We now can put everything on the right hand side. We have theta sub z is equal to 135 minus 5.194, or theta z is 130 degrees basically. If that's theta z, where is that 0? Is it to the right of 1? Is it to the left of 1? Remember, the angle from the pole at 1 to the triangle was 135. We now have an angle that is a little bit less than that. So now it is a little to the left of z equal to 1. The picture is now here. We now know that theta z is 129.8 degrees, and we need to keep several significant digits because we're working inside this small region, which is the unit circle. We know that we're directly above 0.9, and we know how far above we are. We're at 0.1. And we know the angle to get us to that triangle from our 0 location that's given by beta. We now have enough geometry to determine what this x bar, this horizontal distance is. How far to the right is this 0 from the location of 0.9? We know theta z. We know this flat line is 180 degrees. We can use our supplementary angle determination and solve for theta sub z bar. We know beta is going to be this 0.9 plus whatever that distance is, x bar, and that needs to be and will be to the left a little bit of this pole that was due to our PI controller at z equal to 1. I'm not showing the other pole, which was clear over here at 2. Theta sub z bar is the supplementary angle to theta sub z. So we now have 180 minus 129.8, or 180 minus 130 is basically 50 degrees. So now we have 50 degrees is this acute angle, and we can use that with our trig knowledge. We know the vertical height. We just need to find x bar, and we can do that through the tangent. We know the tangent of theta bar is going to be this vertical distance opposite over adjacent. We don't know the adjacent, but we know everything else. We now know that the tangent of theta z, which is tangent of 50, is equal to vertical over adjacent. The only unknown is the adjacent distance. We can solve for x bar. X bar is 0.1 divided by the tangent of 50.19, or x bar is 0.0833. So luckily it's not quite 0.1, because then it would have been all the way to z equal to 1. Now x bar we can use, that's 0.0833 to determine what beta is. Beta is now 0.9 plus x bar, or it's now 0.9833. That's now our PI controller. Or another term that somebody might use for that is a phase lag controller. How does that play into our design? Well, here was our original unstable system. We had a PI controller. We had then that fixed pole at z equal to 1. We now have a 0 right there, and oh boy, what is that? That's our two poles to the right of a 0. These two branches, one goes right, one goes left. They quickly then circle around, and one goes to the finite 0, the other one goes off to minus infinity, and we obviously don't want anything to go outside the unit circle if we can get them both simultaneously inside the unit circle, and we can. But that particular 0 now has been selected such that we end up with poles at these conjugate locations of 0.9 plus and minus j 0.1. What's left? Well, we haven't yet determined k, but you now have everything you need. You have z delta, you have the zeros and the poles. You can now use the magnitude condition to solve for k. So let's find k from the magnitude condition. Here is our controller, PI controller, and here is our plant. So CG's magnitude equals 1. That's the magnitude condition. We can now solve that for k, and we evaluate that expression for our gain at the location that we want our closed loop poles to end up at, which is 0.9 plus j 0.1. And when we do that, we solve for k. We just plug in that complex number for z, take the magnitudes, and we end up with a gain of 1.2. Our PI controller now is 1.2 times z minus 0.983 over z minus 1. That PI controller will actually produce closed loop poles where somebody wanted them, which was at 0.9 plus and minus j 0.1. Maybe that's not the response we want. Maybe we want a faster response. Maybe we don't want them quite that close to the unit circle. Well, what else do we have in our toolbox of controllers? Let's try a PID. We've already tried the PI. Let's go one step further and introduce one more parameter. Now the PID controller gives us two finite zeros, not just one. It does add an additional pole at the origin. But now maybe we can move that root locus a little bit further to the left by the appropriate choice of beta 1 and beta 2. And we would then, the shape of this root locus diagram is obviously going to be determined by beta 1 and beta 2, and that's what we want to learn or be able to adjust or work with in order to achieve maybe more acceptable closed loop behavior. We still have steady state accuracy because we have that pole at z equal to 1. We now can achieve maybe better dynamics by the appropriate choice of beta 1 and beta 2. And they could have been complex conjugates. Here we've made them real, and we know how to sketch the root locus because of our 5 rules.